Welcome. In this video, where we're going to review the great math paper. In my latest video, I implemented the real MVP paper from scratch. In my next video, next Saturday, we're going to implement the math paper from scratch. We're going to produce a self-contained implementation in about 100, 200 lines of code. So very easy to run, very easy to understand. Basically math is a kind of generalization of real MVP. We're going to discuss that in a moment. On very great model. And basically today, autoregressive models are, well, for the last few years, diffusion models have been used a lot. They were the go-to for image generation, for generative AI, for a lot of structured data, such as 2D, 3D, proteins. And today, autoregressive models are coming back and are being more and more common. Normalizing flows as well. They've been used a lot in a bit before 2020. Then they were overtaken by diffusion models. But today, they are more and more like normalizing flow model that are built on the large-scale data sets and that perform as well as diffusion models, okay? So I think it's great to come back to those models. If we dive into the abstract, they say that at the time, autoregressive models were among the best performing models for neural density estimation, together with normalizing flows. And I would say it's still true today, okay? On one side, there is generative AI. So just, being able to generate data from a distribution you've seen and you've trained on. But there is also the density estimation part of things. It's to be able to, you train on a given distribution, then you receive a new data point, and you can estimate the density of that data point, okay? And that's very important, especially in physics, when you want to get the densities of your data points. If you just want to generate images, it's not needed, but being able to evaluate the density is needed in a lot of applications. That's exactly what is said here in the introduction. I was a bit too early for that, but that's exactly what they say. Okay, that autoregressive models, normalizing flow, they provide exact density estimation, as opposed to, for example, autoencoders or diffusion models that provide a lower bound, the elbow. Two great families of models for density estimation. On one side, we have autoregressive models, and on the other side, normalizing flows. On this paper, kind of combine the two. So what they do, they build on the made architecture. Okay, maybe I will implement it at some point. So subscribe for if you want more implementation from scratch of machine learning papers. So basically, okay, maybe for now, let's put that aside, and we're going to come back to that in a moment. But basically, autoregressive models, what do? They decompose the drawn density into a product of 1D conditional distributions. Okay, so you rewrite the drawn density using this this product of conditionals. And basically, the issue is that basically that's what is explained in that paragraph. But if you do that if you want to model that, then you need to do it sequentially. Let's say you have a neural network that models this conditional density, and that allows you to sample from it. So you can sample from P of xi given all the previously generated data. Then you first need to generate x0, and then x1 from x0, and then x2 from x0 and x1. And you need to run a for loop, and you have a sequential process. And of course, with modern GPUs, it's something we want to avoid at all costs. So basically, what's great about the made architecture is that you can generate all the data x, all the xi at the same time in a single forward pass, okay? We're going to discuss in a moment how they do that. But basically, the math paper, so this paper takes advantage of made so that you can model an autoregressive a distribution in an autoregressive way, all in parallel, okay? And basically the way to do that, so let's say you take a fully connected neural network with D inputs, D output, And basically, you will apply a mask on the weight, so you will kill some of the connections. So for example, you will kill the connection between the input 10 with the, between the output 10 with the input 0, with the input 11. So input 11 will not influence output 10, okay? So you mask the weight, and therefore, in a single fault path, because there are a lot of zeros in your weight, output I only depends on input I minus, on all inputs where j is smaller than I minus 1, okay? Yeah, that's what they explain. Normalizing flow, I made a video on that last week. Actually, I have many videos on normalizing flows. Maybe I will put the link in the description if you want to have a look at them. These are mainly implementations. But yeah, basically normalizing flow, it models the density, P of x, by using the change of variable, the change of variable formula. And basically, to be able to compute P of x, you need to be able to compute the determinant of your transformation. So your neural network maps, let's say, u to x. You need to be able to compute the Jacobian of the transformation. So your transformation should be bijective, so that you can invert it, and you can compute the Jacobian of it. Okay, so let's move on. Yeah, okay, that's what we've mentioned for equation 1, so the one we've just seen, to be tractable, so to be able to compute the Jacobian in a tractable way, because there are a lot of neural networks that have the desired properties, but you cannot compute the Jacobian in a tractable way. On, for example, let's say that it takes 1 hour to compute the Jacobian, then if each training step takes 1 hour, you will not be able to train your neural network. So computing a Jacobian should be very cheap and easy to do. Okay, so a common way to model each conditional distribution, so each 1D conditional, it's to model them as a normal distribution, okay? So you model a P of xi given all the previously generated image is a normal distribution with a mean and a standard deviation. That is, or here they model the log variance, okay? So here that alpha is the log standard deviation. So basically they model that with neural networks. So the mean here, you take all the previously generated values, you feed it to your neural network, it outputs the mean on the log standard deviation. And what is great here is that for now, f of u and f of a, that are neural networks, they are unconstrained. Okay, let's come back to that in a moment. Basically, because of the structure of this autoregressive model, because the output I only depends on all the inputs with index below than I, below equal than I minus 1, then if you create the Jacobian matrix, it's a lower triangular matrix, and therefore computing the Jacobian is straightforward. It's just the product of the diagonal terms, okay, by construction. So basically that means that your only constraint, well, by design, there is no constraints, because by design, your Jacobian is lower triangular, and it's very easy to compute the Jacobian. So here, basically, that means that f on, the both function f, they are neural network, and they can be any neural network. There is absolutely no constraint on them. So for example, they can be very complex, they can be transformers with a lot of blocks. There is absolutely no constraint on that. So basically then, when you have modeled the mean on the standard deviation, you can sample from it using the reparameterization trick. So you sample a random variable, you multiply it by the standard deviation, and then you add the mean to it. So that's the fourth pass. You can sample data from this model, but what you can also do is to invert it. So basically, usually sampling, you do that at inference. Once your model is learned, you can map latent distribution to data distribution. But during training, you receive a data distribution that you sample from your unsupervised data. Then you map this data to Z. You compute the, so basically you map your data to the latent space. This is this part of the equation. Then you can compute the PDF of your latent space. you multiply that by the determinant of your Jacobian on basically that gives you P of X using the change of variable formula. Okay, so and then you want to do maximum marginal likelihood. You want to maximize this probability P of X. So that's for so basically during each training you need to be able to invert this equation. You need to be able to go from X to the latent space. On basically those equations, they are easily invertible. You can just rewrite them and obtain U. So basically the random numbers that were generated. Yeah. Okay. Okay. So okay, on basically that was already that was mentioned in another paper. But basically an autoregressive model then can be interpreted as normalizing flow, again, because by construction, you can compute the Jacobian easily. So basically, if we sum up the contribution of this paper, they built a normalizing flow model by using autoregressive model and to avoid sequential computations, so that you don't need to do for loops to go from x0 to xn. They model it in a way that you can do everything in a single thought path, building on the made architecture. Okay. So they show that this architecture, MAF, is a generalization of EAF, so another kind of normalizing flow, and also a generalization on real MVP that we implemented last week. They also show how you can condition it, on making sure that it is sound mathematically, that it does not affect the Jacobian. So basically, I won't spend so much time on that. I will say that it is all for this video. Usually we spend more time on implementation, but I wanted to do this paper review. Let me know if that's useful, if you like it. If yes, I will make more videos like those. Subscribe if it's not already done. And if you like this video, leave a thumbs up. It's really helpful. Thank you.